Okay, so good afternoon. We started our discussion on nucleation from cavities and onset of nucleate boiling in the previous session, and part of which is left that we will be now continuing. So if you recall, this was the last curve where we left. So we were having cavity mouth radius as function of the wall superheat, and we found that minimum amount of wall superheat is required in order for the cavity to be active, and as we increase the wall superheat, we find some spectrum within the minimum and maximum value of the cavity mouth radius, which will be considered which will be acting as the active nucleation sites. Now, whenever we see the process of nucleation, if you recall, earlier we assumed that whenever the bubble was coming out of the cavity, it was actually in the form of a truncated spherical cap. But in real practice, we observe that this type of approximation does not work. So typically, the process of bubble formation and its departure we will see. So if you see at time t equal to 0, we have some vapor volume which is there within the cavity itself, and here at this point we have temperature Tw, and away from this point we will be having temperature T infinity. And because of the presence of the cavity over here, this portion of liquid will be cooler at temperature T infinity, and away from this portion we will be having formation of the thermal boundary layer, where temperature above this thermal boundary layer is actually T infinity. So it means that the portion where bubble is just coming out, in this portion initially temperature is less than T infinity. Now, whenever the bubble just comes out of the cavity, so the period from initial growth of the vapor till the time it just comes out of the cavity is called as waiting period or waiting time of the bubble. Now, you will be finding that in the meantime bubble is just coming out of that, this thermal boundary layer will also progress and ultimately it join each other with small dimple at this particular location. After this point, we will be finding that in this zone now water is having sufficient superheat. So if it is having sufficient superheat and the significant amount of the vapor volume has come and site has become active, then we will be finding that from this point we will be having immediate or say faster growth of the vapor coming out of the cavity. This faster growth of the cavity of the vapor when is taking place, it will be displacing the liquid ahead of this. So when it is displacing the liquid ahead of this, during this period we will be finding that the growth of the bubble will be controlled by the inertia of the liquid. Is this point clear? Because whenever we have something stationary and we have to displace something stationary, then that stationary thing tries to remain at its own location, and if we need to move, we need to push it. So in the similar way, if this liquid has to be moved away by the vapor bubble, growing vapor bubble, the liquid inertia has to be overcome. So in this stage, the growth of the vapor bubble will be actually inertia controlled. We assume that in this range, the temperature of the liquid or degree of superheat of the liquid is sufficient enough, which will not be posing any restriction on the growth of the bubble. Rather, the inertia of the liquid will be actually acting as the resistance on the growth of the vapor bubble. So this initial phase of vapor growth outside the cavity is actually inertia controlled regime. And while it is displacing the liquid, we will be finding that the thermal boundary layer will also try to take the shape of the vapor, and we will be having boundary layer something like this. So this is the T infinity temperature. Now, during this expansion process, as I told you, it is not a complete truncated spherical cap, but we have some interface over here also, and some amount of liquid you can see if I zoom in this, if this is my solid surface, this is the vapor, then in between the solid and vapor I am having some amount of liquid which is entrapped over here. So, this amount of liquid is something which is called as micro layer. So, now what will be happening? The most of the evaporation will be taking place from this micro layer as well. So, whatever the liquid is beneath, because here also we have liquid vapor interface. So, from this micro layer also there will be actually evaporation. Once the bubble shape has become significantly high, after that whenever you will be finding the growth in its size, then rather than inertia, heat transfer rate will also coming into picture, because now if you have sufficient amount of vapor, of course it will be experiencing some temperature decrease because of the immediate transfer of temperature to the vapor medium, and after this point whatever growth of bubble will be taking place, that will be governed by the rate of heat transfer. So, from this point to this point whatever growth is taking place, it is called as heat transfer controlled growth. So, if rate of heat transfer is high, this growth will be faster. If rate of heat transfer is slow, this growth will be slow. And at this stage, the vapor volume is sufficiently high such that, because gravity is acting in this direction, vapor is having lighter density in comparison to density of the liquid. So, if you have a very small bubble, it may remain attached to the surface, but whenever you keep on growing the size, because at surface tension is acting, that surface tension is trying to keep it attached to the surface, but buoyancy force is acting in upward direction, it will try to lift it in the upward direction. So, when the size of the bubble is increasing, the liquid displaced is actually increasing. So, it means the magnitude of the buoyancy force is progressively increasing with increase in the size of the bubble. And when the buoyancy force becomes large in comparison to the surface tension force which is holding the bubble at the surface, this bubble will be actually departing the surface. So, this is called as departure of the bubble, and the complete cycle of the bubble from its initial formation to departure is called as bubble evolution cycle. This is called as evolution cycle of the bubble. So, in a practical scenario, we can see that the initial, there will be some waiting period. Waiting period is the time when vapor is coming out of the cavity. After that, the cavity will be reaching, or say the vapor radius will be actually overcoming the minimum critical radius required for the vapor to grow, and we will be finding that vapor will be immediately growing. Once it is immediately growing, it will be significantly displacing the liquid. So, growth will be inertia controlled, and after some time we will be finding that now the heat transfer effect will come into picture, that rate of heat transfer may not be sufficient enough for rapid growth of the bubble. So, at that time the liquid to vapor conversion will be controlled by the rate of heat transfer. So, that is why we call this regime as heat transfer controlled regime. And once the buoyancy force is greater than surface tension force, then we will be having actually departure of the bubble, and while departure is taking place, some amount of vapor will remain attached in the cavity which will be assisting in nucleation of the next bubble. So, of course, whenever bubble is being departed, majorly it is controlled by the buoyancy and the surface tension forces. But other than that, rate of heat transfer also sometimes plays a significant role, because that is deciding at what rate volume of the vapor is actually growing. So, here we define one non-dimensional quantity which is called as bond number. So, bond number is equal to delta rho into G divided by sigma. So, it is nothing but ratio of buoyancy force to the surface tension force, Fv by Fst. Okay. So, buoyancy force will be nothing but equal to delta rho G. What is the diameter of the bubble which is departing? So, dd cube, because we have to determine volume, and surface tension force will be sigma into, it will be per unit length into dd. So, if I just do the order of magnitude analysis. So, from here I will be finding that the bond number is actually delta rho dd square g by sigma. Now, because it is representing the competition between the buoyancy and the surface tension forces. So, of course, for a surface there will be some critical limit of the bond number above which it will be departing from the surface, and these are some of the correlations which are listed over here for the departure of the bubble from the surface. So, you can find different correlations are there. These are data actually compiled from various literatures, and what you can do is you can see that if you are doing a boiling experiment, you can, if you are doing some visualization of the bubble, you can measure what is the diameter and you can compare with some of these correlations. Now comes the next regime. After nucleate boiling, we have another important regime, because transition boiling stays only for some duration, and typically it's not a long sustainable regime. So, that is why it is not studied much, but film boiling is the one which is actually having practical application. So, that is why the understanding of film boiling regime is also interesting. So, to understand about the film boiling regime, typically it is controlled by two types of instabilities. One is called Taylor instability and second is called as the which typically determine the value of critical heat flux is Kelvin-Helmholtz instability. So, how these instabilities comes into picture? Let us consider that I have a cylindrical tube. In this cylindrical tube, cold water is flowing, and outside of this tube is exposed to saturated vapor. So, what will happen? If I have a cold fluid flowing inside the tube and outside I have saturated vapor, this saturated vapor will give the heat to the tube surface, which will be ultimately carried by the cold fluid. So, ultimately if I have saturated vapor, it will convert into the liquid phase, and soon we will be finding that the entire tube surface is covered with thin film of liquid, and from that thin film of liquid we may find that at certain intervals some droplets are actually falling in the downward direction. Is this point clear? So, what is the reason for falling? You can see simply here, you can simply see here that whenever film will be forming, on this film there can be some perturbation, and when the size of the perturbation or growth of the perturbation is reaching the critical limit, then it will be immediately growing and it will lead to the pinch off of the droplet which will fall from this. And majorly this type of instability is initiated because of the gravitational pull. So, here you can see vapor is having low density and liquid is having high density. So, liquid will try to fall in the downward direction. Now, you can see if I say that on an average basis lambda d is the wavelength of these interfacial waves which are actually forming and growing and leading to the pinch off of the liquid droplet. So, this lambda d is typically the function of surface tension force, gravitational force, gravitational field and the density difference between the two. So, if I simply perform the dimensionless analysis, I will be finding that lambda d into g rho f minus rho g by sigma becomes nothing but equal to some constant. Okay. So, typically the value of this constant is observed to be 2 pi root 3 for one dimensional waves, and it is typically found to be 2 pi by root 6 for two dimensional waves. Okay, so one dimensional wave means a wave in which you will be having dimple all throughout the entire plane. But if you have dimple in this plane also, so then the nature of the wave will be becoming two dimensional. If pipe is placed vertically, in that scenario we observe this type of behavior. The top portion of pipe will be having some lesser thickness of liquid film, bottom portion will be having more thickness of the liquid film. And while this liquid film is moving downward, if I have some strong vapor movement over here, then that vapor movement may lead to formation of small droplets. But majorly because the downward situation is favorable for liquid to travel in the downward direction. So, as we will keep on moving in downward direction, the thickness of the liquid film keep on increasing. Is this point clear? Now, in film boiling regime, what happens? In film boiling regime, the entire periphery of the heater surface is covered by the thin vapor film, and from some specific locations the pinch off of the vapor volume takes place and number of bubbles rises in upward direction. So, this is the photograph of a film boiling regime, and it is nothing but a reverse situation to that of this. So, here this is my raw vapor and this is raw liquid which is stagnant, and because of the lighter density bubbles are rising in upward direction. So, typically for film boiling process, the minimum wavelength which will be required for instability to grow, that is G rho f minus rho g sigma square root equal to 2 pi. So, with this number it is actually scaled. Now, this can give me the idea that at what locations bubbles will be actually pinching off in the film boiling regime. Now, there is one more instability which is called as vapor column Helmholtz instability, and this instability is very important for defining the critical heat flux. So, basically what is critical heat flux? Critical heat flux is the departure from nucleate boiling regime, and immediately after that we enter into the film boiling regime by following a transition regime. Okay. So, we know that near the critical heat flux, the number of nucleation sites which are active on the surface are significantly high, and from multiple nucleation sites when vapor is forming, these vapor will actually merge together and form the large column like structures. Now, when these column like structures are formed, these are having some surface waves. Okay. At certain time, it may so happen that the amplitude of this surface wave is so high. So, typically what will be happening here, you can see here you have liquid and here you have vapor. This vapor is moving in upward direction and this liquid is moving in the downward direction. So, there is some velocity difference between the vapor side and the liquid side. So, what does it will do? Whenever you have a velocity difference across an interface, then the instability which defines that whether this wave will be dying down or it will be growing, that particular instability is called as Kelvin-Helmholtz instability. So, you can observe that if you have a planar heater surface, on a planar heater surface, the wavelength, particularly the wavelength at which columns will be appearing, that is decided by the Taylor instability. Okay, because bubble is rising because of the buoyancy, so that is decided by the Taylor instability. But when these columns are rising, these columns have certain surface waves, and these surface waves can either increase, their amplitude can increase with time, and two waves can merge together to form a single vapor chunk, or if this amplitude is diminished, then this will keep on moving as a vapor column. If it is keep on moving as a vapor column, my nucleate boiling regime will keep on continuing. But if this instability grows, then what will happen? If two vapor chunks are joining each other, water will not get entry, water will not get sufficient area through which it can penetrate to the heater surface, and in the meantime entire heater surface will be blanketed by the vapor medium. So, we need to define that. Once from the Taylor instability we were able to find that what are the locations where these vapor columns are forming, then we need to decide that whatever these waves are growing, say lambda h is this wavelength. So, what is the critical velocity of the vapor column at which these waves will become unstable and these will merge with each other, because the critical wavelength, so the critical velocity at which these will be merging, our liquid will not reach and we will be entering into the transition and the film boiling regime. So, it means our critical heat flux condition will be immediately reached. So, for that purpose, if we do the linear instability analysis, we find that the critical value of the velocity is nothing but 2 pi sigma divided by rho v lambda square root. So, this is the critical velocity. If velocity of vapor column we are able to maintain below this, then we will be able to continue boiling in the nucleate boiling regime. If we go above this, then we will be immediately shifting to the transition and film boiling regime. Now, one more thing, I have earlier mentioned you that if LB and L are comparable, it means that the size of the heater is comparable to that of the length scale of the bubble. In that scenario, what will happen? In that scenario, we will be finding that immediately whatever the vapor volume will be forming, it will be completely enclosing the entire heater surface. So, there will be nothing like nucleate boiling. Immediately whenever we will be initiating the boiling, we will be entering into the film boiling regime. So, this situation also happens in certain scenarios. If you have to do boiling on an extremely thin wire, say of 0.5 or 1 millimeter diameter, and if you are boiling water, then corresponding length scale of the bubble will be close to 2.73 mm, and we will be finding whatever vapor is growing, that will be encapsulating the entire surface. So, that type of situation actually I have shown over here, where our interest is to study the boiling heat transfer over a cylindrical wire. So, this is a cylindrical wire of extremely small diameter, and on this cylindrical wire you can see that we have given some rotation also in the counterclockwise direction, and that rotation is quantified in terms of the Reynolds number of the vapor. So, vapor Reynolds number is defined as density of vapor into angular velocity. So, this velocity is basically r into omega, where r is the radius of the heater surface and omega is angular velocity, and then length scale will be diameter of the heater surface divided by viscosity of the vapor. So, if this way we define the Reynolds number and we are giving some counterclockwise rotation, we are trying to study what effect it will produce on the dynamics of the bubble. So, here you can see initially there is formation of a vapor volume, and whenever the time is progressing, along with the progress of the time, the amount of vapor volume produced is actually increasing. And because of the rotation, if there is no rotation, then vapor will be producing in the form of a symmetrical structure. But because of the rotation, this structure is slightly asymmetric. Vapor is trying to shift towards the leftward direction. That is not our major objective. Our interest over here is to study that during this vapor formation and its departure, how our heat transfer coefficient actually varies. So, what has been done? The surface averaged Nusselt number has been defined, and if you calculate the surface average Nusselt number, its value is 10.25 here, and you can see when the amount of vapor volume is increasing, its value is actually increasing, and once the vapor has just departed, it again started decreasing and reached almost to the initial value, and after that this cycle will keep on continuing. That is what you can observe here in this graph. So, from this lowest point, initially heat transfer coefficient has increased, reached a peak value, and then it has decreased, again reached a peak value and then decreased, and this process is actually continuing. So, it means a number of bubbles are actually leaving the surface with the progress of time. You can observe two interesting features. The maximum value of heat transfer coefficient is corresponding to the situation when bubble is just about to depart from the surface. The reason is, whenever this bubble is about to depart, it is pulling maximum amount of vapor in upward direction. So, when it is pulling maximum amount of vapor in upward direction, the thickness of the vapor film, around the heater is actually lowest. So, when you have lowest thickness of the vapor film, the thermal resistance will also be lowest, and we will be having highest value of heat transfer. And in the other situation, when it just departed and vapor have just started accumulative, the buoyancy effect is not that high that it can pull the vapor in upward direction, and the thickness of vapor film around the heater is actually more, which decreases the overall thermal resistance of this system. So, it means that in a film boiling regime, when the bubble just pinches off from the surface, corresponding to that we can achieve the minimum value of the vapor film on the heater surface, and corresponding to that situation we can have highest value of heat transfer. And when vapor is growing over the film, corresponding to that thickness will keep on increasing and the heat transfer coefficient will be less. Now, this is something which is tried on two surfaces. So, here d is the diameter of the heater surface and lambda naught is nothing but the length scale of the bubble. So, when it is maintained 0.5 and in another situation it is maintained 1.5. So, corresponding to 1.5, of course, the length scale of the vapor bubble will not be changing, because we are not changing the fluid combinations, ultimately we are changing the diameter of the heater surface. So, if we take a larger diameter heater surface, there the area available for heat transfer will be more, and corresponding to that we will be having higher value of heat transfer coefficient, whereas for smaller diameters the value of heat transfer coefficient is actually less. We do have there also cyclic behavior, but the minima and maxima in heat flux is less in comparison to minima and maxima which is obtained for the larger cylindrical surface. Another interesting feature, you can see that because we are not changing the fluid combination, so that is why what will be happening, if we are not changing the fluid combination, the vapor volume will almost depart at the same diameter. Okay. And if heater surface is large, then the vapor influx will be more for larger diameter case in comparison to vapor influx for smaller diameter case. So, this is the reason the number of vapor bubbles in a given time which will be forming for larger diameter will be more in comparison to the number of vapor bubbles found for smaller diameter. So, here you can see the cycle time of single bubble evolution cycle is more for smaller diameter, whereas this cycle time is actually smaller for the larger heater surface. Is this one clear? Now, this is one interesting parametric variation. So, what we can do is, we can have a cylindrical heater, a circular heater, or I can also make, so sometimes it may come to my mind that instead of using a circular heater, let me go for an elliptic heater, because if I go for this type of elliptic heater, ultimately it will be increasing the overall area available for the heat transfer, and it may also give some picture, it may also give some feeling that because it is this particular shape is more slender in comparison to the bluff shape. So, circle is a bluff body, but this type of body may appear to us as nothing but a more like a streamlined body. Okay. So, whenever vapor will be moving over the streamlined body, it may move faster in comparison to its movement on a bluff body. So, here what we have done, this red colored thing is the actually cylindrical heater and blue colored thing is actually elliptical heater. And these multiple ellipses we are forming by keeping our this, if 2b I take the width of the minor axis of the ellipse, then this b we are keeping identical to that of the diameter of the cylinder. But what we are increasing this value of a major axis of the ellipse in order to achieve different aspect ratios. So, here you can see when the aspect ratio is 1, corresponding to that the peak in the Nusselt number is highest, and of course, the entire curve of the Nusselt number is actually at the top. and when my aspect ratio is 0.4, it means I am moving more towards the elliptical body. Corresponding to that, there is decrease in the overall peak of the Nusselt number. What is the reason? The reason is, if you see a cylindrical body, in the cylindrical body, when this bubble is rising, the neck of the bubble is formed more closer to the heater surface. Once it is formed more closer to the heater surface, the thickness of the vapor film will be actually less around the cylindrical heater. But in case of an elliptic heater, where bubble interface is represented by these dashed blue lines, here you will be finding that the neck is forming significantly away from the heater surface. So, because of this, the thickness present, though area is more, but the thickness of the vapor film which is present around the heater is actually larger. So, this has actually resulted in lesser value of heat transfer coefficient. However, if you see the overall period of bubble formation and its rise, that is almost 1.5 times to that of the period for the cylinder shape. Okay. So, though we will be getting lesser heat transfer coefficient, but the number of bubbles which will be forming at this surface will be actually more in comparison to the number of bubbles which are formed on a cylindrical surface. And the reason is quite obvious, because a bluff body will be providing more restriction to the flow in order to it will make it difficult for the bubble volume to rise in upward direction. In the meantime, cylindrical shape, this elliptical shape will be having more preference for the volume to rise in upward direction. Now, after this one topic we will very briefly we will discuss it, because this is just for the sake of completeness. Whenever we do talk about the boiling heat transfer, particularly the flow boiling heat transfer, because in majority of the say industrial applications, whenever we are using refrigerators, whenever we are using our coal based thermal power plants, whenever we are using our nuclear power plants, everywhere we actually have some evaporator tube somewhere, then we have some condenser tube somewhere, and in between we have some devices and we have to pump the working fluid through that circuit. So, and typically mostly in the nuclear industry this is even more challenging. We know that in nuclear industry it is very difficult to control the rate at which actually heat is added to the working fluid. And if there is any accidental situation that say your pump has stopped working, so in that scenario what will happen? Your coolant will not be circulated. If coolant is not being circulated, in that scenario you will be experiencing loss of coolant, and suddenly whatever the water is there or any type of coolant is there, that immediately will get converted into vapor, and once it has converted into vapor, dry out will happen, and this will lead to the overheating of the system, and there can be even its meltdown or other type of failure. So, typically one of the approach nowadays people have started thinking, even this is long back people are using, that instead of using the pump we can utilize the density difference between hot and cold portions of the tube for allowing flow to happen. Similar type of application you may find in thermal management of electronics. So, one of the important device which nowadays we are using is named heat pipe. So, heat pipe is also having the flow of working fluid through this density difference. So, in natural circulation systems, the density difference between hot leg and cold leg will be actually deriving the flow to take place. For example, if you have an arrangement something like this, this is the hot portion, this is the cold portion, and you have some working fluid. So, this working fluid will be actually gaining heat in this portion. After gaining heat, because of its, so once it is gaining heat, its density will become less. So, once its density is becoming less, it will try to move in the upward direction. Once it is moving in upward direction, it will displace this heavier liquid, and this heavier liquid through this leg it will start moving in downward direction. So this will initiate certain flow, but this flow is not that easy because it will lead to large number of instabilities. So of course it may appear very easy for us that by just maintaining the density difference we can allow flow to happen, but these flows are subjected to a large number of instabilities. So that is one of the primary reason that despite its simplicity and no requirement of any additional pump, such systems are still not implemented in scenarios where actually even failure is one of the critical issue. So few advantages of this system is that it offers simplicity of design and economy of the operation because you need not to run pump. Another thing, it may find applications in commercial power generation, but it has extreme challenges, particularly which can be addressed by its proper design and operation procedures. So circulation rate, the working fluid, the rate at which it is circulating, that is called as circulation rate. So circulation rate of the working fluid is not known a priori to us. Okay. So for example, in a pumped system, what happens? If you start pumping the water, we know that how much discharge pump will be giving at the given pressure drop conditions. Okay. But if you use a natural circulation loop, you will keep on heating it. You will not be knowing in advance that at what point of time flow will initiate and how much amount of flow rate we will be getting once the natural circulation loop has started. So flow rate is not known in advance. This is one of the major disadvantage. However, it depends upon whatever amount of power we are supplying, because depending upon the power, heating will take place, and other many parameters such as operating state and geometrical configuration of the system. Generally, these type of systems are more susceptible to instabilities because of their inherent flow feedback. What is the meaning of inherent flow feedback? Let us assume that at some point of time, one vapor bubble has started forming. So this vapor bubble will keep on growing, and it may so happen if growth of the bubble is rapid, it will be entirely blocking the path. So if it is entirely blocking the path, then what will happen? Immediately the flow behind this will be stopped unless or until some next disturbance is coming to initiate the flow. Okay. So whatever the resistance of the system is dynamically evolving because of the formation and immediate condensation of the bubble, that will be actually immediately affecting the flow rate which is coming from the back side. Okay. The resistance and restriction is not constant. It all depends upon the way different phenomena are taking place within the tube. But still, people are actually trying to study this, and whenever people are trying to study this, the major interest is to study the two-phase flow instabilities which takes place inside the natural circulation loop. So some of these instabilities are mainly classified as microscopic and macroscopic instability. Microscopic instability means if you have a evaporator, so because of the bubble formation, whatever waiting period of the bubble, or due to such microscopic issues, whatever instabilities will be actually developing, these comes under the scenario of microscopic. And in terms of macroscopic instabilities, this system is actually entirely coupled to large number of components. So when it is coupled to large number of components, then whatever flow reversal you are observing or fluctuations in the flow rate you are getting, so whatever the changes in bulk parameters are taking place with time, these comes under macroscopic instabilities. We also have static and dynamic instabilities. Any type of instability which can be explained by steady state analysis, that is called as static instability. And the stability which requires temporal term to be accounted for in order to fully analyze it, that is called as transient instability. And compound instability is whenever any two or multiple type of instabilities joins together and affect the entire flow, that type of instability is called as compound instability. Now, some of the instabilities are named over here. We are not going into that much details. Of course, all these instabilities depends upon the nature of loop geometry, number of unstable zones, disturbances or oscillations which are taking place in the system. Of course, these are some of the characteristic curves which we will skip. Yeah. So, let us now try to see subcooled flow boiling instability. What is the meaning of subcooled flow boiling instability? So, again I will be taking a system. So, my system is identical to the one which I explained you earlier. I have a vertical tube over here, and this vertical tube is actually acting as heater. So, here I am actually heating the working fluid, and then here I have one condenser, and after condenser here I am again recirculating the working fluid to the heating section. Of course, in actual arrangement above the heater section we need to keep a large height riser section so that we can actually achieve the necessary head. So, now when we will be heating the working fluid in this heater, what will happen? This working fluid, because of decrease in its density, it will be rising in upward direction, and from here it will be falling in downward direction. So, typically the conditions which we are considering, here you can see along this side I have plotted mass flux. What is mass flux? Mass flow rate of the working fluid divided by cross sectional area of the tube is called as mass flux. And on the right hand side I am plotting temperature. So, the red colored line over here is actually representing the value of saturation temperature corresponding to the local pressure of this heater section. So, whatever is the pressure of the heater section, at that point whatever is our temperature, that is actually saturation temperature, and the blue colored line is representing exit temperature of working fluid. So, when exit temperature of the working fluid is less in comparison to saturated temperature, it means what is our boiling process? It is nothing but the subcooled boiling process. And why I am calling it boiling? Because I explained you earlier that if my heat flux is sufficiently high, in that scenario what will happen? Even in the bulk of the liquid or core of the pipe, even if my liquid is in subcooled state, I will be having formation of small bubbles at the periphery of the heater surface. Is this point clear? So, all these bubbles now will be rising in upward direction, and when these will be rising in upward direction, because ultimately these are mixing with the, at the center these are mixing with the subcooled liquid, these bubbles will not be able to sustain. So, once these are not able to sustain, these will be condensing before reaching to the exit, and at exit whatever the overall temperature of the mixture we will be getting, that will be less than the saturation temperature. However, these bubbles have actually done some task. What task these have done? These have initiated the flow. Once these started rising in upward direction, these initiated the flow in the entire circulation loop. Now, as I told you that we will not be having constant value of the flow rate, we will be having oscillatory flow rate. So, here you can see this mass flux over here is actually of oscillatory nature, it is not fixed. So, if I have to apply this in any practical scenario, I need to design the system in such a way so that the amplitude of these oscillations is as low as possible, and I should be able to get some unique average value of the flow rate during the entire period. So, the instabilities which typically takes place because of this effect, these are called as actually subcooled flow boiling instabilities, and the major reason for occurrence of these instabilities is actually partial developed boiling. So, what is the meaning of partial developed boiling? All the bubbles have formed, but immediately after that these have actually condensed. If you see the temperature profile, you will be finding that, so typically we measure the temperature at different sections of the heater. So, the temperature values is shown over here. So, here you can see this is the saturation temperature line, and here you can see that the wall temperature is actually initially increasing. At some point of time, wall temperature has suddenly started decreasing. The point at which there is sudden decrease in the temperature is actually the point where a bubble has nucleated and it has just left the surface. So, because of the bubble nucleation, what will be happening? It will be taking significant amount of heat from the wall, which is equal to that of latent heat of vaporization required for that bubble mass, and a decrease in the wall temperature is known. So, whenever we see a decrease in the wall temperature, this particular point is called as onset of nucleate boiling. At this point, nucleation of the bubble has started. However, this bubble will not be able to sustain, but once we again found that after this decrease, the wall temperature has again started increasing. What it means? That bubbles are forming, and these are not just collapsing at the moment, but these are growing at the moment. So, once these start growing at the moment, it means now we can say that our saturated boiling has started. Okay. So, this is how we can actually distinguish the regimes between nucleate boiling and the saturated boiling. Then this is another situation where we are having saturated flow boiling. So, here you can see the exit temperature of the water is actually close to the saturation temperature. Okay. But it is not throughout close to the saturation temperature. For some instant it reaches saturation temperature, then all of a sudden it falls. Why it is falling? Because the situation when it is maximum, corresponding to that your mass flow rate is minimum. Okay. So, when temperature is reaching close to the saturation temperature, corresponding to that mass flow rate is minimum. But again, when suddenly mass flow rate will be increasing, so significant amount of liquid will come immediately. So, this significant amount of liquid will then decrease the overall temperature at the outlet. Is this point clear? So, this type of instability is called as saturated flow boiling instability, and if you see the pressure drop versus mass flow rate characteristics, you will be finding that corresponding to situation when temperature at outlet becomes equal to saturation temperature, I will be getting the two phase mixture. But the situation when the temperature is falling below the saturation temperature, I will be getting the single phase liquid. So, it means that my fluid will continuously keep on translating from high quality zone to low quality zone, and low quality again the high quality zone to low quality zone. So, it will keep on oscillating between single phase and the two phase regime. Yes, yes. So, saturated temperature is fluctuating. All of a sudden what will happen? Vapor has started coming. Once vapor starts coming at the outlet, the vapor will be expanding also, because what is its volume is significantly less in comparison to the, its density is significantly less in comparison to density of liquid. So, all of a sudden vapor will expand. When vapor will be expanding at the rapid rate, then it will be creating significant pressure drop. So, corresponding to that you will be experiencing fluctuation. Third type of instability. So, this is I think wrongly written over here. It should not be subcooled flow boiling. This is the situation when we are operating in the saturated regime, but sufficient amount of vapor is forming, and this vapor is actually leading to the periodic dry out at the temperature at the wall of the heater surface. So, whenever I will be having periodic dry out at the heater surface, corresponding to that you may consider that a significant amount of vapor has produced. So, once there is significant amount of vapor, that will be all of a sudden expanding and it will be closing the entire portion of the tube. Once it is closing the entire portion of the tube, the pressure in the vapor side or outlet side of the heater will become larger in comparison to pressure at the inlet side, and in this scenario I will be finding some sort of reverse flow. So, here you can see when significant amount of vapor starts forming, then we get the reverse flow. So, instead of moving water in the forward direction, water will also start coming in the backward direction. Okay. And what is the consequence? The consequence you can see, whenever vapor is forming at heater surface, you are supplying continuously electric heating or any other type of heating, but vapor is not able to take the heat. So, there is sudden rise in the temperature because of the sudden rise in wall temperature because of the dry out. And whenever you are able to cool, like flow has established, liquid has just quenched the heater surface, then you will be finding significant decrease in the wall temperature. Here you can see that in case of subcooled boiling, my heater surface temperature is a fixed value. In case of saturated boiling, because some of the vapor, some portions of the heater surface will be covered with vapor bubbles, you can see small fluctuations in the heater temperature surface. But whenever we are having the occurrence of the periodic dry out, like all of a sudden significant amount of vapor is producing, which is completely covering the entire periphery of the tube, there we will be having sudden significantly high rise in temperature, and during re-wetting process significantly fall in the temperature. So, our heater surface will be subjected to periodic rise and fall of the temperature. So, these are some of the issues which one need to address with natural circulation flow boiling before their implementation in the actual industrial or practical systems, because if we do not address such issues, then though their idea was to actually avoid accident which could take place because of the failure of the pump, but these may cause actually accidents if these instabilities are not avoided. Yeah, so maybe let me now discuss this. So, this was the system when I am simply considering the instability in the heater surface. But if I consider the entire system instability, then the situation become more complicated. Let us not discuss this. If you people are interested, you can refer to this source which is given over here. So, this reading material will be actually, this material will be provided to you. So, maybe I will stop at this point here. So, if you have any questions, that we can discuss.